There we go. So yeah, let's go ahead and get started with this week's topic, which is all about gamma rays. So my name is Leah, and I'm a second-year PhD student working at the University of Michigan with Dr. Sarah Pozzi. And today I'm going to be discussing gamma ray interactions. And tomorrow, another PhD student is going to be discussing gamma ray detections. So this might be a little bit of a review for some of you. It might be an entirely new topic for some others because we have a wide range of experience at our summer school here. So keep that in mind. And a lot of it too could be a review from last week as well, because Ricardo did a good job of explaining gamma rays as well. And if you have any questions, you can just throw them in the chat and we can address those at the end of the lecture. Yeah, okay, I think that should be good. So let's get started with learning about gamma rays. Hold on one sec, there we go. So let's start off again with some review of what gamma rays actually are. So gamma rays consist of these packets, and I'm going to be calling them photons or gamma rays throughout the rest of this lecture, with electromagnetic energy in the highest energy level of the electromagnetic spectrum that we can see down here. So the gamma rays fit down in this area here, where their frequency is about 10 to the 19 hertz, and their wavelengths are about 0.1 nanometers. And gamma rays originate from transitions within the nucleus itself to lower lying nuclear levels. So if we look at this beta decay spectrum for cesium-137, we can see that as our cesium decays, we get a gamma ray emitted at an energy of 662 keV. And the primary, the gamma rays are produced primarily from nuclear reactions, including fusion and fission, but again, also radioactive decay, such as the spectrum that the decay scheme I just showed you as well. One thing about gamma rays to just briefly mention is the type of radiation they are. So gamma rays are a quote unquote harder type of radiation, meaning this is pertaining to their ability to penetrate thicknesses of materials. So if we look at this diagram down here, we can see that gamma rays are less affected by self-absorption, and they can penetrate other materials that alpha particles or beta particles, for instance, cannot. So that's why when we are doing experiments in nuclear engineering and nuclear physics, and we want to use shielding for gammas, lead is a very nice and common type of shielding for gamma rays themselves. Now I'm going to briefly touch on the difference between X-rays and gamma rays. So again, both consist of these packets or photons of electromagnetic energy within these higher levels for the EM spectrum. But a big thing, like the major difference between how to categorize gamma rays and X-rays is their origin. So, we can see from the spectrum right away that gamma rays typically include these photons that are of higher wavelengths and higher energies than X-rays, but a big thing to distinguish between the two is how they are created. So gamma rays themselves are created within the nucleus, whereas X-rays are produced in the electron cloud. And this can happen when electrons strike a target or when the electrons rearrange or de-excite within the atom themselves. So again, we are going to be talking about gamma rays mainly for this, and not to be confused with X-rays. Now, there are three main interactions that can occur for gamma rays, and the first that I'm going to talk about is the photoelectric absorption. So photoelectric absorption occurs when this incident photon or gamma ray undergoes this interaction with a bound electron within the absorber atom, and it transfers the full energy to what is called a photoelectron. So this diagram is very useful for this. So we have our incident photon come in, it interacts with our atom, and then this electron or photoelectron is emitted. And the energy of this photoelectron is equal to the incident energy of the photon minus the binding energy of that electron. So this interaction takes place within the atom itself, and the photoelectron is ejected from wherever that electron's bound shell was, typically like the K shell. And because of this, this also can create this ionized absorber atom, and from this, it actually can go and the vacancy of that electron can be filled through electron capture or rearrangement of the electrons themselves, and an X-ray is emitted from this. So for photoelectron absorption, also called photoelectric effect, you might have heard of that term as well. The predominant mode for interaction occurs when we have our incident photon for low energy gamma rays. And this is enhanced with the high atomic number, so the Z value for the absorber material. So the higher you go in Z, the more likely that this can occur for you. And its probability is proportional to that Z, that high atomic, or just the atomic number of the absorber material over its energy, the incident energy of the gamma ray to 3.5. And N can vary between 4 and 5 usually. So a common thing to put is just 4.5 for this factor right here. The next type of interaction we have is Compton scattering. So Compton scattering occurs when a photon interacts with a free or weakly bound electron. This is the only type of interaction that doesn't necessarily need a observer atom to be there, because this can happen with free electrons as well. And when Compton scattering occurs, the photon transfers a portion of its energy to what is called a recoil electron. And then that gamma ray is deflected or scattered, so it still remains. So this can occur for all scattering angles possible, and therefore the recoil electron energy ranges. So tomorrow in detection, we'll learn about the Compton spectrum, basically, where we can get a wide range of electron energies depending on its angle. And our equation, in order to find out, one, what the energy of the scattered photon is, and then this can also help with us finding the energy of the recoil electron, is right here. So we have our energy of our scattered photon is equal to our energy of our incident photon over 1 plus our incident photon energy over mc squared, which is the rest mass energy of the electron, so 511 keV. And that is all multiplied by 1 minus cosine theta, where the theta is the angle between the scattered photon and that incident photon as well. And from here, we know that the recoil electron energy plus the scattered photon energy is equal to our incident photon. So if we have this value, we have this value, we are able to calculate what that energy of our recoil electron is. And Compton scattering is the most often predominant interaction mechanism for a wide range of energies for just radioisotope sources. And its probability depends on the number of electrons within the material, as well as it increases linearly with the Z of the material as well. And our last mode of interaction we have is pair production. So pair production occurs within the Coulomb field of the nucleus. It's not necessarily within the nucleus itself, it's near the vicinity of it. And what happens is the photon disappears, and in its place, we get a electron-positron pair. So this diagram here, we have our incident gamma ray coming in near the nucleus. It disappears, and then electron, positron emitted off. Now, for pair production, the incoming energy has to be greater than twice the rest mass of the, or the rest mass energy of the electron. So there is a minimum threshold that it has to have 1.022 MeV in order to even be able to occur. And so because of this, pair production is more likely to occur when we have these higher energy incident gamma rays coming in. And the excess energy shared between is shared between the positron and the electron if it is greater than the 1.022 MeV. And sometimes the positron can then annihilate with a different electron, and then two annihilation photons are created from that as a secondary product to this entire pair production process. So again, pair production is the predominant interaction mechanism as our energy increases into a lot higher energies in MeV, and the probability for this varies as the atomic number squared. So to summarize briefly the three modes of interaction that we just went through, this is a really nice diagram to look at if you just want like a quick visual of which do you think is going to occur. So as I mentioned before, for photoelectric absorption or photoelectric effect, the predominant mode is for these lower level gamma ray energies, and it is enhanced with the high atomic Z number. So if we look here, we got our low level energies, we go up in our Z of our absorber atom, we get the dominant area. Compton scattering, the energy ranges, as you can see here for this x-axis from 0.01 MeV all the way to 100. And again, this goes up as well with Z with the high atomic number. And pair production, because we have that minimum threshold that we need to, or not threshold, but that minimum energy that we need to get, this is more dominant in these higher instant energy values. And these lines right here just mean that if an energy or an atomic number lies within this line, it's a equal probability that it could be a photoelectric effect or a Compton effect. So if we have like 100 keV and 20 is our Z value, it could be either. Now, because this is a summer school, we're going to do some practice problems, but because it's summer, I'm going to go through the answers with all of you. So our first example problem we have is we have a 1 MeV gamma ray incident on bismuth, and that has an atomic number of 83 and a binding energy of 4.3 eV. So from this, some interaction is going to occur, and 0.6 MeV electrons are going to emerge. So is the electron produced by photoelectric effect, Compton scattering, or pair production? So I've included the equations that are relevant for this problem, so we don't have to go back in slides. Again, the photoelectric effect, the photoelectron is equal to the incident energy minus the binding energy. And Compton scattering, we have our scattered photon is equal to this equation with our incident photon and its scattering angle. And then pair production, this is the energy of the electron and positron being shared, which is equal to our incident photon minus, again, this 1.022 MeV. So why don't we take a couple minutes to work this problem out? Some of you might have already got it done already. But we'll take 2-3 minutes maybe to go through the calculations, and then I'll go through them with you together. while we're going through this problem, I see that there are some questions in the chat quickly about pair production. So let me read those quickly. So in pair production, is it possible to create any, whoops, sorry about that. Is it possible to create any other particle-antiparticle pair if the incident gamma energy is much greater? So I'm going to preface and say, I don't know. I want to say no, but I could imagine when you have high energy gamma rays, multiple interactions can occur, depending on if it's scattered first and then pair production. But the fact that you're asking if there are any other particle-antiparticle pair, I don't know. I'd have to look that one up for you. That's a good question, though. Okay, so why don't we go ahead and talk about this problem? It's been a couple minutes. So let's go through each of the different interactions and see if it would make sense. So the first we have is pair production. So pair production is actually a little bit easy to eliminate because we know that our incident gamma ray energy is 1 MeV. And right away, we know that 1 MeV is less than 1.022 MeV, so this cannot occur. So we're able to cancel that one out right away. The next one we're going to look at is photoelectric absorption. So I gave y'all the binding energy of our bismuth as well as the electron energy produced. So this would be the energy of the photoelectron given off. So if we look at our equation again, what should happen is our incident energy is equal to our binding energy plus the energy of the photoelectron. If we do the math, we see that this does not occur. 1 MeV is not equal to 4.3 EV plus 0.6 MeV. So we know that this is also not photoelectric absorption. So that means that Compton scattering must have occurred. So if we go through and we use our Compton scattering equation, we know that we know our HV value, and just from doing the math of 1 MeV is equal to 0.6 MeV plus 0.4 MeV, we know that our scattered photon is equal to 0.4 MeV. So if we plug this into our equation down here, we would be able to check out our theta value for the angle that it was scattered at, which comes out to 76.5 degrees. So this is an example of Compton scattering. Now, some of you might have just thought back and looked at this and saw that what's most likely to occur, where's the dominant area? Again, we have our incident photon, 1 MeV right in the middle, and our Z value is 83. We go up, it fits within this Compton effect area. Now, if I would have changed my incident energy to 10 MeV, for example, or like 1 MeV, or just kidding, 0.1 MeV even, this could change the effects drastically. And again, depending on what I changed our electron energy to. So yeah, that's just like a fun example of how to try and figure out which type of interaction can occur with a gamma ray. And now we're going to go to our second problem. So this is a Compton scattering problem. So we have a gamma ray of energy 662 keV, and that is Compton scattered by an electron. And I want to know what the minimum energy of the scattered photon can be. And I also want to know what the maximum kinetic energy of the recoil electron can then be. So again, I included this equation down here for us for reference. And again, we know that the incident photon energy is equal to the energy of the recoil electron plus the scattered photon. So why don't we take a couple minutes again to do this one. and then we can come back and work on it together. Oh, I see something in the chat real quick. You said electrons plural. How about for photoelectric effect, we emitted n number of electrons as in your first question? I think I might have misspoke or mistyped that. No, for the photoelectric absorption one, it's just the incident photon and then the one scattered photoelectron. How about if we emitted n number of electrons? I don't think that you can emit multiple electrons from the one photoelectric absorption interaction. Yeah. We'll give it maybe one more minute. I see another pair production question quickly in the chat. In pair production, is the sharing of energy equally distributed? Yes. So the excess energy that comes from the incident photon is equally distributed to the positron and the electron. Okay, so why don't we go ahead and work on these problems? So again, we have our incident photon 662 keV, Compton scattered. What is our minimum energy of the scattered photon, and what is the max kinetic energy of our recoil electron? So these are the answers that you hopefully got. And We got 184 and 477 keV for both of these. So if we go and do the math with them, what is the minimum energy of the scattered photon? Again, we want the minimum energy, so that would occur when our denominator is at its maximum. So if we want this to occur, we want our angle to be 180 degrees, because then our cosine theta is -1, 1 minus -1, we get 2. So then we have our HV over 1 plus HV mc squared times 2. And if we do the math, we get our 184.34 keV. And we could have gone through and did the math again, but a nice way to to think about this is if we have a minimum scattered photon, we're going to get our maximum recoil electron. So again, we know this. We also know this from the problem. We can use our equation again and rearrange it to see that 662 minus this value is 477.65 keV. And if you got that problem right, that's good. This was actually a candidacy exam question on one of the 2018 nuclear engineering candidacy exams for University of Michigan. So if you got that right, you're on your way to getting your PhD. The last thing I'm going to talk about briefly are just some gamma ray applications. So gamma rays are very applicable in medical physics, including radiotherapy, ionizing radiation treatments for cancer. You might have heard of PET scans or using gamma rays to kill cancer cells and tumors. Here we have a visual right there for that, for the medical physics side. So these are very applicable. Also sterilization. So gamma rays are actually used for surgical and medical equipment in order to sterilize and clean them, as well as for food preparation. And it can kill bacteria and help the food stay fresher longer. This does not make the food radioactive. I'm going to throw that out there in case there's any confusion about that. But yeah, this is also for food safety. Gamma rays can also be used for security and imaging. So here we have like a cargo truck, and the scientists use gamma rays in order to see that there were people on there. And then just like Homeland Security as well. Gamma rays have lots of different applications for those. And some common sources that are gamma ray emitters that are used in many applications are cobalt-60, cesium-137, and technetium-99, the metastable. I think that's how you say that. But like cobalt-60, that one's really good for the medical field as well as the food preparation and sterilization. Cesium-137, for a lot of the nuclear engineers in here, that's a very good energy calibration source. We use that one a lot in our lab because we know the energy of the gamma emitted. It was actually the 662 from the previous problem, as well as the Compton edge, which was that 478 keV as well. And this one, the technetium, this is the most common gamma ray emitter source for the medical diagnostics and like the medical field in general. It helps with brain and liver and I think bone and a whole bunch of different medical applications for this one. So that one's really common as well. And with that, so we ended a bit early on this lecture. Again, to summarize, gamma rays go through three main modes of interaction. We have our photoelectric absorption, where incident photon comes in, interacts with our bound electron, and then a photoelectron is emitted. The incident photon is completely absorbed. Compton scattering, the incident photon is not completely absorbed. Part of the energy is transferred to this recoil electron as well as a scattered photon. And again, this can happen with weakly bound electrons, free electrons as well. And then we have pair production where we have our incident photon interact near the vicinity of the nucleus, and it has to have a minimum energy of 1.022 MeV in order to distribute its excess energy as well to a electron and positron pair that can go and interact with other things, or the positron can annihilate as well and produce annihilation photons. So with that, like I said, we ended a little bit early. So if there are any questions y'all might have for me, I want to go back and do more problems, I could think of some for us. But other than that, yeah, thank you. So I will go ahead and look at, okay, I'll go through the questions now. Oh, this is good. Back to my one question where someone asked if there could be other particle-antiparticle pairs in pair production. Someone mentioned, Daniel Jackson from Lanel mentioned 2-muon and anti-muon, or tau and anti-tau could be created if energy of photon is high enough. Okay, good to know. Thank you for today's lecture. You're welcome. Is there a maximum energy an electron can carry? I mean, I want to say yes, within like just the bounds of physics. I don't know the maximum energy. Oh yeah, here we go. No, as it gets close to the speed of light, energy diverges. Daniel Jackson knows what's going on. Let me see the other questions we have. Thank you for today. Whoops. I don't know why that happened. Hold on one sec. My neighbors have a dog. I don't know if you guys can hear that as well. I apologize for that. Okay. Where? Okay, sorry, the chat like went away for a little bit, and then I got distracted by my neighbor's dog. That's Zoom life though. Pair production probability decrease. Okay, pair production probability decreases for the very high energy incident gamma rays. Is it because they have very small interaction time? I should have really studied up on pair production. You guys are quizzing me for this one. Is it because they have very small interaction time? Let's go back to again, for this question, I want to say yes. Yeah, so this question, they're referring to these higher energies and why this value is not as dominant. Yeah, and I think Compton decrease. Uh, okay, you mentioned weakly bound electron can also cause Compton scattering. I happen to know that Compton scattering can only occur with a free electron because momentum and energy are conserved. Can we prove that for weakly bound electron too? Okay. I got that information from my nuclear physics book, so maybe I misread it. Can we prove that for a weakly bound electron too? Probably not in right now. Can we prove that for a weakly bound electron too? Yeah, I'd have to think about that one for more than the couple minutes we have right now, but all these questions have been very good. I'm going to put in my email as well so we can discuss these later. There. If anyone has any questions that I could take a little more time to look at because I don't want to give the wrong information. Oh, someone messaged them as well. There we go. It occurs both free and weakly bound electrons. The free case is just an approximation. Perfect. Well, yeah, if those of you that don't have any other questions can feel free to hop off. Yeah, and I'll stick around again to try and answer more Pear Production or otherwise questions. But again, my email is in there as well. So if there are any strong concerns or questions, please feel free to email me. But yeah, thank you for coming, and make sure to tune in tomorrow for our gamma ray detection, where our PhD student Nora is going to be talking about how to detect gamma rays and also different types of detectors, which are more useful or not useful depending on the applications as well. So yeah, thank you for everyone. I know we ended a bit early, so enjoy your afternoon or wherever you happen to be for this summer school as well.